Hi everyone. Today's topic, today and Friday, and as I said earlier, and in the weekly plan. So instead of the usual recordings on Friday, to end the class nicely, we will actually have a live session. It will also be recorded, so if you can't attend, you can view the recording afterwards. And both of these lectures will be on derivatives and differentiability. Specifically of multivariable functions. Okay, so an outline, rough outline for today. We'll talk about the main issue that you have with differentiability, and the issue revolves around different ways of approaching the origin, and that is already explainable quite nicely in the context of limits. And in that context, we'll already see the main examples that will come up. So there will be no derivatives in that case. We'll just talk about limits, something that really brings us back to where we started the course. And then we will introduce, based on those issues that we saw with the limits, we'll introduce three versions of differentiability. And we'll talk a little bit about their relationships by phrasing some theorems. We won't today prove theorems. Friday will more focus on proving them and what kind of techniques come up there. Then we will talk about examples showing that these are actually different things. So the question that I want to start with this warm-up on limits is that, well, what is the limit as x, y approaches 0, 0 of a function of two variables? If you want, you can imagine more components here, is 3 dimensions, or x1, x2, ... xn. But trust me, all of the issues with differentiability already appear in 2 coordinates. So if you understand the 2 coordinate case, you really understand everything. So there's no need to really talk about, in these examples, about higher dimensional things. So, well, what is the definition of limit? Well, if your point gets closer, then the function values gets closer. So we say that this limit is equal to whatever, if for every epsilon positive, there exists a delta positive, such that if the distance from the point xy to 0, 0 is less than or equal to delta, and often, depending on book, you'll have also not equal to 0, 0. If you are so close and not quite equal to that point, then your function value will be close to the limit value that you want. So, and the intuition here is, and there's actually a theorem to this avail, that what is this saying? This is saying that if you get close enough to some delta ball, then your function values will be close. But this is independent of the direction that you're doing. And these aspects, how it's independent of the direction, once you're close enough, all of these play a role, and these are good to focus and think about them. So to emphasize this, let's ask some stupid questions. I mean, these are stupid because all of them have answer no, but actually thinking about why they have an example no is actually very important for this differentiability discussion to understand what's it all about. So suppose I have a function of 2 variables, and suppose if I approach 0, 0 along the x-axis, so that the limit of this one-dimensional limit is equal to f0, 0, and suppose if I approach on the y-axis, suppose I knew that both of these would be equal to the function value. So the first one here is approaching, well, the first one is on the x-axis. And then the second one here is on the y-axis. Is it then true that your 2-dimensional limit is equal to the function value? So this is coordinate-wise. Well, the answer is no. And the reason is that the other directions are not controlled. You can approach along the axes and the function will approach that function value. But if you approach any other direction, then you get a different value. So other direction is not controlled. So it's fairly easy to come up with functions where the axes are controlled, and everywhere in the other four quadrants, if you're strictly inside of them, you can do anything. So one example is fxy is equal to 0 if you're off the axis. So function value 0 would be in these quadrants when neither of the components are 0. And then you'd equal 1 on the axes. So that's what this function is doing. So if you take the limit as t goes to 0 of ft0, well, what you get is you're looking only at the axes, you only see function values 1. So this is the case. And similarly, if you approach on the other axis, you get 1. But the limit as xy approaching 0, 0 of fxy does not exist, because along some sequence of points you get 0, and in another sequence of points you get 1. So maybe this is a point where we can recall this theorem statement, the sort of sequential definition of limit. We say that limit xy approaching some point x0, y0 of fxy is equal to L. This is true if and only if for any sequence of points xn, yn that converges to x0, y0, we have that the limit along that sequence is equal to L. So really, you get this idea that limits as the point approaches 0 are really thinking about any way of approaching. And if you only control the coordinate directions, you're not controlling the diagonal directions. Fairly simple. Well, let's say that we actually also control the diagonal directions. So the next question then is about directional limit. So suppose I took a limit as f of, for all k in real numbers, I took a limit of fkt times fktt. So what am I taking the limit of? These are good to draw as a picture. So as k varies, I'm varying the line along which I'm taking a limit, k being the slope of this line, and then I'm converging along that line. I guess technically, if we draw it like this, then tk. So we're approaching along those lines. And what if we assume that for every fixed line, the limit is equal to f0, 0. So for all these lines, technically this avoids the y-axis, so you'd have to assume it additionally. But since this is just an example, I don't want to make it too technical. And the question is, does this imply that the limit holds? I mean, you might fairly think that, sure, it should, because now I'm controlling every direction. But the answer is still no. And the reason is that we are not controlling all the ways of approaching 0. We're still insisting, okay, the points can approach from any direction, but what if they approach somehow in a curvilinear way, tangent to some direction, Or what if they somehow weirdly spiral in? Okay, spiraling in actually you could preclude. So the only bad case really is something like the approach is tangent to some direction. But that is a little tedious to prove. So let's see this in action. So one example is, and you get a pattern of these examples. They often look like something divided by something. You play with the different parts, what you put in them. And I should have no, this is right. So this is when you're not at 0, you're a ratio of these two things. And at 0, 0, you are equal to 0. So this is the function. Now, let's compute the direction of these. If we fix a k in real numbers, well, the limit as t goes to 0, so along this slanted line that we drew here, is f of t, tk. And now what is this? This is now t is non-zero because we're approaching 0. So we plug that into the definition of the function. In the numerator, we get t to the 5th k. In the denominator, we get t to the 6th plus t cubed k. Well, what is this? We take out a factor of t cubed from everything. We get, t cubed from everything. So we are left with t squared k, t cubed plus k. So when we send t cubed to 0, this factor goes to 0. Okay, there's one small case. When k is equal to 0, you're already 0. And when k is not equal to 0, either way, this thing will go to 0. So this limit is always equal to 0, which was equal to the function value. But as said, this is only controlling the linear directions. What if our sequence of points approaches somehow along a parabola? So consider a sequence of points, x and yn, which is given by 1 over n squared. Well, let's see what is now the limit along this sequence. So not in this direction, but along this sequence. Well, this would be x to the 4th. So 1 over n to the 4th times y. So 1 over n squared. Then we have x to the 6th. So 1 over n to the 6th. And plus y cubed. So 1 over n to the 6th. So what is this? On the numerator, if you have 1 over n to the 6th, you divide by twice that. So this is limit of 1/2 is equal to 1/2. So we see that this function is actually not even continuous. It's not continuous. And the limit does not equal this two-dimensional limit that we were looking at does not equal the function. That is correct. You should have k cubed here. Yeah, thank you. It doesn't affect the calculation. Thank you, Bowen. Yeah. So there was a typo here because it's tk to the cubed. K should be to the cubed. Either way, you get 0. Good observation. Other questions? So the way to think about all this is that there are 3 ways of approaching 0, and there is one along the axes. There's 2 along lines, and then there's kind of a third way, which is every way of approaching to 0. And that's what this double limit is talking about. a side note here is that you might remember, if you did 32A a long time ago, some of you years ago, there was a test that you used to prove that a limit exists. And it actually was that you did this calculation for all k. And then you were told that, okay, after you've done it for all k, you're basically done. Well, no, this counterexample shows that that's not sufficient. So you really need to work more carefully if you actually want to prove these limits. So this ends our warm-up on this limits.